In a previous video, we showed why several quadrilaterals cannot be cyclic quadrilaterals. And we did this by discussing the basic properties of several of these shapes, leading to us understanding that it wasn't possible for the shapes to be cyclic. The most basic requirement is that the opposite angles of a quadrilateral must add up to 180 degrees or be supplementary if they are to be a cyclic quadrilateral. In this video, on the other hand, we're going to discuss the few basic shapes that must be cyclic quadrilaterals. These are those shapes, and we'll go through them one by one and discuss why they must be cyclic quadrilaterals. The three blue ones are quite simple, and the yellow one is a bit more difficult, and we'll call that a bonus shape. We'll do that at the end. I'll also be discussing why these three shapes share similar properties which cause them all to be cyclic quadrilaterals. They do look different, but they do share a specific properties which make them more likely to be cyclic. Well, we can start off with the square and rectangle because essentially they have the same properties. Each of the angles in a rectangle is a right angle, and each of the angles in a square is a right angle, which is 90 degrees. So if you add any two angles in a rectangle or a square, because your first angle, let's say we're choosing A and B, your first angle equals 90. In fact, let's choose A and D, and your second angle D equals 90. And if you add A plus D, that's going to give you 90 plus 90, and which equals 180 degrees. So A plus D equals 180 degrees, and for each shape, A and D are opposite angles. So it's quite clear that the sum of opposite angles in a square or rectangle is 180 degrees. And so both of them have to be cyclic quadrilaterals, and this is why, as you can see, for the square, all of the corners lie on the circumference of the circle, and we get the same result for a rectangle. All four corners of the rectangle lie on the circle, so it's a cyclic quadrilateral. The next shape that we're going to consider is the Isoceles Trapeziod. Really, it's just like an isosceles triangle, as you can see, but with the top chopped off, which creates two parallel lines, one at the top and the base, but it is a symmetrical shape. And actually, the fact that it's symmetrical helps us to prove that it is a cyclic quadrilateral. I'm going to draw the line of symmetry, and you can see that the left-hand side of the shape is just a mirror image of the right-hand side of the shape. Let's label all of the angles. So we've got A, B, C, and D, A and B on the top and C and D on the bottom. But because the left side is a mirror image of the right side, we could rewrite the angle B because it's just a reflection of A, and we could rewrite the angle D because it's a reflection of C. So then we could say that B equals A because they're the same angle, and D equals C. Now this symmetry will help us to show that opposite angles in the isosceles trapezoid are supplementary, that they add up to 180 degrees. And let's do that by finding the sum of all the angles in the trapezoid. We have the angle A, then we have the angle B, but we said B is the same as A, so we can add another A plus C, and then we can add D, but remember D equals C, so we add another C, and that should equal 360 degrees because that's the sum of angles in a quadrilateral, which means that 2A plus 2C equals 360. We can factor out the 2 from the left-hand side of the equation, which means 2A plus C. 2 times A plus C equals 360 degrees. And if we divide both sides by 2, these cancel, and that gives us that A plus C equals 180 degrees, which should make sense, right? Because the shape is symmetrical, and A and C are sum of half the angles in a quadrilateral in which the sum of all angles is 360 degrees. So A and C should be 180 degrees. But what if we want to find the sum of opposite angles to find out if the trapezoid is a cyclic quadrilateral? Well, we would do A plus D, right? Because A is opposite to D. But we can rewrite this because we've already shown that D equals C. They have the same value, the angles are the same size. So really, this is just A plus C, and we know that to be 180 degrees. So the opposite angles in the trapezoid must add up to 180 degrees, which means that this quadrilateral is a cyclic quadrilateral, and it's quite obvious to see anyway because you can see that the four corners of the quadrilateral lie on the circumference of the circle. So the isosceles trapezoid is a cyclic quadrilateral. Now, the isosceles trapezoid and the rectangle and the square have some things in common, which I think is what makes them cyclic quadrilaterals. And that is that all of them are symmetrical and their lines of symmetry are similar. If we add a line of symmetry for the rectangle and then we add a line of symmetry for the square, we can take a look at the similarities. You should be able to see that each shape is symmetrical about the vertical line, which means that the right hand side of the shape is just a reflection of the left hand side of the shape. You can see this with all three. The line of symmetry is like a mirror and it just reflects one side in the other side, which means that for all three shapes, for example, the top right angle is just a reflection of the top left angle. So in the rectangle case, B equals A, and it's exactly the same for the square. The top right angle is just a reflection of the top left angle, and the same for the trapezoid. And again, for the bottom angles, it's exactly the same thing. So the bottom right angle is a reflection of the bottom left angle. For the square, the bottom right angle is a reflection of the bottom left angle, and it's the same thing for the trapezoid. They basically are a reflection of each other. And because the angles are just a reflection of the other side, that means the sum of angles in the left side of each of these shapes is exactly the same as the sum of angles in the right side. And because the line of symmetry splits the shape into two halves with two angles on each side, the sum of the angles on the left side of these shapes must be half of the sum of the angles in the entire shape. So because these are quadrilaterals, the sum of angles, let's call them SOA for sum of angles, equals 360 degrees. But because these angles on the right are a reflection of the angles on the left, the sum of the angles on one side is half of the sum of angles in the quadrilateral, which means that in each case, A plus C must equal 180 degrees. But I'm not going to call them A plus C, I'm just going to call them the top angle plus the bottom angle equals 180 degrees. But because the quadrilateral is symmetrical about the vertical line, the sum of any top and bottom angle is 180 degrees. For example, in the square, the sum of this top angle and this bottom angle equals 180 degrees, that's A plus C, but the sum of this top and this bottom must be 180 degrees because this bottom here, D, is exactly the same value as C. So the sum of any top and any bottom angle is 180 degrees. And because the sum of opposite angles is really just the sum of a top angle and a bottom angle, here's an example. These two angles are opposite, top and bottom. These two angles are opposite. That's the sum of top and bottom. With the rectangle, the sum of opposite angles is these two, A and D. One's the top, one's the bottom, and the same with B and C. One angle is the top angle and the other angle is the bottom angle. And the sum of top and bottom angles equals 180 degrees. From that, we know that the sum of opposite angles in a quadrilateral, if they are symmetrical in this way, must add up to 180 degrees because top and bottom angles always add up to 180 degrees. It doesn't matter which side of the symmetry they're on. This is the top, this is the bottom, that's the top, that's the bottom, and they add up to 180 degrees. And that's a way in which all of these quadrilaterals are similar and why we can easily prove that they are cyclic. The final quadrilateral we're going to deal with is this one. You can see that it's four-sided. In the previous video I called it a diamond, but it's actually a kite with its own special properties, which I won't go into for this video, but you can already see that this must be a cyclic quadrilateral because all of the corners of the quadrilateral lie on the circumference of the circle. But I just want to go through a quick proof to show why that is so. It's based on this circle theorem where the angle in a semicircle is always a right angle 90 degrees. I've made a video previously discussing exactly if you're interested in knowing why this is true. But we can use this to prove that the kite is a cyclic quadrilateral. What I'm going to do is recreate the diamond using angles in a semicircle. So let's put the first angle in the semicircle. So this triangle has a hypotenuse which goes through the center of the circle. Each end of it is touching the circumference. And then the angle opposite the hypotenuse is touching the circumference of the circle. This angle is always a right angle, so this angle is 90 degrees. But what if we viewed the diameter or the hypotenuse of the circle as a line of symmetry and we did an exact reflection of this angle in the lower semicircle? Well, then you get this angle in the bottom of the semicircle, and this angle is the angle in a semicircle. So this, the value of this, is 90 degrees because it's a right angle. But now if we look at the entire shape, we've got a kite shape. It's a quadrilateral, there's four sides, 1, 2, 3, 4, and it's a shape of a kite. But because of the angle in a semicircle theorem, this angle is 90 degrees and this angle is 90 degrees. These are opposite angles of the kite. That angle is opposite this angle. There's two more angles that are going to be opposite each other. But if we now take the sum of these two angles, we get 90 degrees plus 90 degrees, which equals 180 degrees. So the sum of these two opposite angles is 180 degrees. So this must be a cyclic quadrilateral, but it's a kite. So a kite is a cyclic quadrilateral. Now we might have to be careful a little bit on this one because let's say you had a kite like this. Sorry, my drawing's not very good, but this was 95 degrees and that was 95 degrees. Well, then that adds up to 190 degrees. So this wouldn't be a cyclic quadrilateral. So in order for this to work, you have to use the theorem where the angle is in a semicircle, the angle is touching the circumference of the circle. And then when you reflect the angle in the lower semicircle, that will make a kite shape, and that will be a cyclic quadrilateral.